UMass in Amherst in Western Massachusetts. I think we've known each other since about 1998.
90 something.
1990 something.
Yeah.
And I think I first visited him in about 2000 when I spent some sabbatical there.
Yeah.
We worked together quite a bit. Eliot has got a phenomenal reputation for his work in systems generally, particularly things like garbage collection, which he's going to talk about today, but also things like persistence,
Transactional memory, which I'll also mention along the way.
and so on and so forth. And he's the joint author of my second book. We started in about 2006 talking about it.
Yeah.
It came out in 2011. Now, being gluttons for punishment, we decided to do a second edition.
Right.
And so he's been visiting and we've had his nose to the grindstone.
Right. Thank you. You let me know if you can hear me. I expect people in the room will be able to. I hope people online will as well. So yeah, it's a pleasure to come back and talk here. So I'm going to present almost exactly what I presented at the International Symposium on Memory Management back in June. They kindly invited me to offer a keynote sort of toward the end of my career, so I decided to look back. I'm officially retired, but I'm still doing things, as Richard pointed out. My wife would say she hasn't really noticed the difference. We'll see. I'm flunking retirement, I suppose. Right. So just a quick thing about what this talk is and what it isn't. So it is personal observations. So you see a bunch of opinion along the way. So it's not your usual research talk backed up with loads of evidence. But I hope you'll find it useful or interesting. And it's mostly from the point of view of projects that I've personally participated in or have some direct knowledge of. It's not a comprehensive survey of the field or everything that's gone on since I wrote my first garbage collector or things like that. Neither in terms of topics or things that have been built or even the people who built them or even the things I personally have been involved in. I did not try to be comprehensive, but I hope interesting. So, points I hope to make. One is that garbage collectors, memory managers, automatic memory management in general is hard to get right, especially in the kinds that we have in modern systems. People demand concurrency, they demand low overhead, they demand high degree of reliability. And I observed that concurrent GC algorithms have always been what I call the poster children for difficult, subtle proofs of concurrent algorithms. And this dates back to articles I remember reading as a graduate student in communications of Kcml back in the 70s, when Kcml was one of the premier technical places you would see papers about new algorithms. Another point I hope to make is that good tools and good methods can help with this, and so we ought to use them. One matter of influence is the language in which memory managers are written. Another is the software engineering approach taken and the degree of discipline that the software engineers use in doing that. I hear stories, I haven't always seen the code myself, of where people had a great idea, but it was not enforced, and the end product, the rules are broken all over the place to where the system is very difficult to change in certain ways. You end up with a 500,000 million line code base, and you just don't know what you can change without breaking something somewhere else. This is also an area in which we know less about the performance limits than many other areas do. We don't necessarily know how fast the best memory manager could go for a particular program. The worst case analyses are not very helpful in practice because they're way off from what a particular program might require. And so often we just don't know how much we might be able to improve. On the other hand, garbage collection has been very successful in getting the overhead, in many cases, down below 10%, below 5%, whatever, for many programs. Of course, that It's getting in the realm where other things probably matter more. So I'm going to do this a little bit sequentially through history, not totally, but my first collector that I wrote, because I have a little story about it. It was a Mark Compact collector, as I recall. I don't have the code anymore. I don't know if anybody has the code anymore. It was along about 1978, maybe. But it was the first collector written for the Clue programming language. Who knows Clue? Nobody. Right? Yeah, one or two. Okay. And it was a straightforward, stop the world, whole heap collector. Based on a Mark Compact algorithm. Now, just for fun, the machine was a PDP-10. So this is a series of machines developed by Digital Equipment Corporation, and they liked octals, so things often came in multiples of 3. So you had 18-bit addresses, and then this machine had 36-bit words. So a word could represent a cell to 18-bit addresses. So it's kind of nice for writing Lisp and all. So a lot of the AI folks love this machine. Anyway, it was naturally challenging to debug because I was writing in assembly language. Now, the thing that I remember was that I had a problem where it would crash during the third garbage collect for some test program I had written. And it was really hard to figure out what was going on. I had to trace back through and eventually discovered, after about a week of effort, full days, that the error had happened in the first GC. But it corrupted some object that the program hadn't used again until later, and then kaboom. So these things can be often very difficult to track down. By that time, because it's a Mark Compact collector, the object had moved twice. The addresses that weren't the original addresses. And it turned out that in this case, I was able to use a really nice feature of the debugger tool at the time, where you could trap on accesses or updates to particular addresses. Something that, curiously enough, a lot of the intervening time, most debuggers did not support that between then and now. So many do now, GDB. Anyway, so lessons. It helps to come with a strong design that's been well critiqued. We did a lot of discussion of this with we're trying to write out invariants on the blackboard and so forth in the research group. Be precise about what was supposed to be happening. Another lesson is know your tools and know how to apply them. It would have taken a lot longer without that knowledge of how to use that debugger effectively. And maybe assembly language isn't the best tool for writing garbage code. And this was a simple one, imagine the ones today. You may have snippets you have to write in assembly code, but we hope that there are not many and not more. And I'm sure there are other lessons and strategies that come out of this. But, that's how I got on the road, so to speak. So part one of this talk is learning how to do GC well, not just me, but the community. So it's hard. Now, I mentioned those papers in the Kcml, and because people found them to be interesting algorithms and the fact that they were correct was pretty subtle, they often made correctness arguments in the papers, which is a good thing. And then 5 years later, someone came along and showed that correctness proof, the hand correctness proof was wrong. But this is not a wonderful state of affairs. Now, I'm not dissing those people. It was good work. They were doing their best, but it's really hard. And so the sort of people who made mistakes are people like Guy Steele. No slouches. And anecdotal evidence, you talk with, say, Java implementers or whatever, Java virtual machine implementers and all. The intricate things around, say, finding pointers in the stacks and registers and many other things in especially concurrent memory management are one of the largest sources of bugs in their system and hard to find. And there is a sense in which it seems that this may have stifled innovation in memory management. Because they get something that's working and they deploy it and they don't want to mess with it. They don't want to put in, really advanced, tricky algorithms because they know they're going to be sources of bugs that then you're going to have to devote a lot of support effort to. Okay, so what do we do with that? By the way, I should say, feel free to interrupt. We can be kind of informal here. When I was giving this back in June, it was a Zoom talk, so it's like I'm talking to a screen. Here, we've got some people we can interact. One thing we can do is better tooling. So that might be languages and so forth. I'll mention one or two things. Better ways to deal with these subtle algorithms and build our confidence that they're correct. 1A here is this idea of toolkits. So let's roll forward a bit, 12 years or so maybe, to 1990 or so. I'm a junior professor engaged in building a small talk virtual machine and things like that. And someone in the research group, I'm not sure I can claim responsibility for it, had the idea of writing a more language-independent toolkit for building garbage collectors. Because we had built a generational scavenging one for small talk, and then I think at the time we were thinking of working on some other language and said, hey, could we borrow that over and use it? So how would we do that? Something would be language independent. Now, here I mean the client language to be supported, but not the language in which the garbage collector is being written. That would all be one language. In this case, it was C. It might not be my choice today, but it was a reasonable choice then, perhaps. And the main thing was to have a very clear API. Think about that very carefully. What are the concepts? What are the things you can do with them? And we separated out the discovery of roots, where the pointers were and the global variables and the stacks and the registers. Well, that's something for the client language to know about, because we're not going to impose on them what their structure is for their objects, their stacks, and so forth. But that part, the client had responsibility for. Once they tell us the roots and tell us enough about the layout of the objects, we could go trace through and do the right thing. That was the idea. So it supported Stop the World multi-generational copying collection, also called scavenging at the time. You could decide how many generations you want. It's easy to build, say 4 generations if you thought that was a good idea. People were playing around with those ideas then. I think most of the time now, you really only see 2 or maybe sort of 3 generations, like a permanent generation. But it seemed like an interesting idea then. It's the first attempt I'm aware of, specifically making it easier to write garbage collectors for future language implementations and implementers. Because up to that point, everybody would roll their own. Implement, I design the language, write the compiler, build a runtime system, write my MVC. A lot of work. And probably most still do that, which I claim is needless, that we can come up with ways to have a common shared infrastructure and not do so much. Toolkit idea. So some of the reasons I'm in favor of it. It can reduce the implementation effort for managed languages. We kind of saw this. There was this thing, a spate of language design scholars, the one I think of first, where people said, oh, Java is out there, it's managed language, it's all these complete libraries, networking, garbage collection, all of that stuff. I don't have to write that, provided I can compile to Java bytecode. Design my new language, compile to Java bytecode, get all these features. Sounds like a pretty reasonable idea. Problem is, the Java virtual machine has Java-ness baked into it. You kind of have to wedge your ideas into Java class hierarchy ideas, which is not always a wonderful fit. It seems to kind of show through with Scala sometimes. In other languages, it's even harder. But the idea is that you get reduced implementation effort, which is certainly true. And if we do a toolkit and invest a fair amount of resources in a nice toolkit, it can give you a range of options. You could have copying collection, you could have mark sweep collection, you could have concurrent, non-concurrent, generational or not. You could offer lots of options, whereas if you're building it all yourself, you'll get tired, you'll run out of time or money. So that's an advantage. Already debugged, perhaps somewhat tuned, any system probably needs a little bit of its own tuning, but people might have some good experience with it. These are some reasonable settings to start with. A clear API helps improve the maintainability of the overall language implementation. The compiler writer knows what API they're targeting. The other parts of the runtime system know how they have to interact with the memory manager to make things work right. So you get a more modular system with more separation of concern. And if you have quality code written by experts, you don't have to be an expert in GC. You have a good collector for your language. So you don't have to become as expert in as many things to have a good implementation. So those are some of the benefits. Some of the challenges. One is there's huge diversity of languages and their runtime environments and their implementation strategies. How do they do stacks? Do they have global variables? It goes on and on. Also, it's typical to need some degree of customization to the hardware instruction set, especially in the concurrent world. Are you going to use compare and swap? Are you going to use, what's the alternative?
Load, link, store, conditional.
That's right, yeah, load, link, store, conditional. So the variety of things like that. Are you on a machine that has weak memory ordering, where you have to put in fences and things like that? And then also you might need customization to the operating system in terms of what it lets you do with memory mapping and things of that nature. Different languages sometimes have special requirements or special opportunities. Functional languages offer some particular opportunities because they're mostly non-mutating. So you can design collectors in ways that say, okay, you want mutable objects, you'll pay more burden for that. But if you're writing a system for Java, most objects are expected to be mutable, so you can't bias against that. Right. Java also has its reference types, the weak references. There's 3 flavors of those, plus finalization. We've been rewriting the chapter in the book just this week, so it's on my mind. It's very complicated. It's hard to get right. And then dynamic languages. So there, some of the issues are, you've got more dynamic code loading, maybe even garbage collection of code, garbage collection of types, or the layout of an object changes because a new field gets introduced. You think in Python, someone assigns to a new field, whatever, and then it gets created in the dictionary. And then there continue to be more and more different GC algorithms and techniques. We've got an expanding diversity there, so that's a challenge for a toolkit project. And in the modern world, we need to offer at least some concurrent memory management options. Those are trickier. Now, some other challenges, less technical perhaps, has to do with a lot of people, they want control to say, I'm not sure I want something that somebody else wrote. I want control over it. Or even if they like it, I'll say, well, my company won't let me do it because of intellectual property issues, because that thing's open source and we don't do open source, or whatever it might be. Inertia. It's like, oh, I'll have to adapt to this thing, or I have to go figure it out, or whatever. Lack of knowledge, they don't know about it. Hubris, like, I can do it better. It wasn't invented here, so it can't be as good as what I could do. None of us ever are guilty of that. Now, moving forward about 10 years from that original idea, Steve Blackburn, a colleague of ours, some of you may have met him or know who he is, very active in GC work, and he's at the Australian National University. So he was a postdoc working with me on a large National Science Foundation project called Kcml. And I say large, at the time it was big, it was a little over $1 million for 5 years. He undertook to rewrite the collectors that were in JICE RVM. So this was the research virtual machine that IBM had developed. And originally we got a non-disclosure type license from them, and then eventually they open sourced JICE RVM, which is a great thing that they did for the community. But the original collectors had been written, well, let's put it this way, not in a very Java style. It was sort of like the guys wrote C with Java syntax, more like the flavor of how they built it. And part of that was, the engineers, they weren't, long-time dyed-in-the-wool Java programmers or even object-oriented programmers. I'm not criticizing them overly, but Steve felt that we could do better rewriting these collectively. So he rewrote the runtime system in Java, but what we call restricted Java. So there's some Java features you can't use if you're trying to write a garbage collector. One of them would be allocation. Right? You can't assume automatic reclamation because it hurts your building. So if you take Java and throw away some of the features that require allocation, and then you add in some others to let you explicitly manipulate addresses and bytes and pointers and stuff, then you get R Java, which is what this was coded in. And then that got rewritten a little bit later. Steve was less involved in it, but he was kibitzing, I guess. Harry Cheng from IBM and Catherine McKinley, I think she was still at UMass at the time, but she might have moved on. It was around that time. And there they followed the strict discipline of using Java interfaces, Java classes, class hierarchy, and clear set of concepts. So they exploited the hierarchy. They avoided premature optimization. They said, let's go with clean ideas and then see how fast it runs, and we can tune it. They introduced, and this is what I was talking about before, these special types like address and byte and word and so forth. So these became intrinsics that they smartened the compiler up to know about. They could generate the code that you would expect. So you load to an address, and it really just turns into a load. Right, so it's unsafe, right? It breaks Java safety in R Java. But you write a garbage collector, you're writing unsafe code anyway. You might as well write it in a good language for writing unsafe code instead of a weak one like assembly language or C. Then Steve got the idea a little bit later of, oh, well, we could take this idea and try to make it more language neutral, a little less Java centric. It was still written in R Java, but could maybe support other languages. And I don't know, do you remember, Richard, what other languages or implementations? You got it into somebody else, at least one other JVM besides Jax RVM, but I'm not.
Yeah, I can't remember.
Can't remember about other languages off.
Yeah.
That was the idea.
I mean, I got the impression that not many people. There was a IBM had a big, I mean, a lot of people wrote it.
Yeah. Yeah. He had some, like one or two other industrial people.
Yeah, I just didn't try to go doing.
Yeah. But anyway, I mean, you can see that the idea is that this concept is maturing, decade by decade. And this had many more algorithms, components, and concepts, and it's kind of a tinker toys, we would say, or I guess it's a mechano or something in British speak, right? The tool set for building GCs, and it sparked a wide range of GC research using the Jax RVM. Some of the conclusions I draw about toolkits, this line of research showed that they do simplify language implementation. They can speed innovation and exploration. Once that toolkit was out there and it was open source, hordes of graduate students started inventing different things. It's really powerful for research anyway. It can offer good performance and can actually serve a range of languages, that's been shown. And this tends to enhance the robustness, not just of memory management itself, but because of the way memory management is so fundamental and the way you get a nice clean separation, it tends to enhance the robustness of the whole implementation. 7 points. You can see you can write in higher level languages pretty effectively and in a fairly portable way. And this has been known for 15 years or more. So opinion. I think it's past time for industry to go on board with this concept. It's been improved. There was at least one product. Ravensbrück did a thing. I'm not sure too much came of it. Sort of, there was a paper in ISMM around 2000,
they were very
and then just
keen.
sort of.
They were very keen for other people to use it, but
Yeah.
they really jumped on board.
Right. It wasn't as general as NOTK as I
It
recall.
never too clear.
Okay, now, some caveats about toolkits. So I'm bullish on them, but there are issues. New ideas might fit the structure that you've put together, or they might not. It's hard to know. And so there will be limits on which languages and runtimes a toolkit can possibly work with, or at least work with very easily or effectively. They're going to need continual growth and revision. So I think it's something like this, if it evolves into a community thing, is going to need the same kind of support that, say, GCC or LLVM or something like that needs, ongoing maintenance and support as the whole language universe evolves. Right, so community effort would be great, open source, maybe coordinated with LLVM for good compiler integration, and so forth. The future. Steve is actively working on a new iteration of MMTK written in Rust. And he has some neat ideas there. So I'm sure you'll be seeing things coming out in the next few years. And this code, this Rust code, and I showed this personally, it can link efficiently with any language compiled with the LLVM toolchain by using link time optimization in the implementation. So you can write out in Rust all your little code sequences and so forth, and then using link time optimization, the compiler, or actually the linker is invoking the compiler optimization passes, can inline them very effectively. Now, the strength here is in the good design in the API, and of course, the competent implementation of it. You still have to have discipline. Little caveat, LLVM, maybe not exactly a JIT yet. Yeah.
One which you kind of alluded to, I think the other thing, apart from toolkits that made PC so accessible, is that now we have a good language talking about things. We talk about variants and things like tricolor systems is an object, black, grey, white. The community generally knows what means. We talk about user program and mutator in the same terms as the black, grey, white mutator.
We've developed terminology,
Yeah.
ideas that are in common.
Talk about barriers of different kinds. And that gives people a common way of understanding quickly what's going on, and that's really helpful.
Right.
I mean, the problem I think with MMTK, and I think that's where it founded a bit, it was very much based around supporting JAX RVM.
Right.
And when IBM started supporting the sort of, others didn't do a lot of development on the Java side, if you like.
Right.
Making it fast. And
yeah, having to keep pace with the industrial strength. Yeah.
Then it sort of ended.
Right, right. Yeah, so the hope is that getting this over in Rust and not so associated with a specific language implementation or even a specific language. Right, okay. And we can go farther than just memory management toolkits. We can talk about how this idea is expanded into language toolkits. And again, I credit Steve Blackburn with a lot of this, but I enthusiastic supporter of the ideas. So he designed something called the MU, or micro, virtual machine. And this combines the memory management, threads and thread stacks, and an intermediate representation just based on LLVM IR, but adjusted a little bit to better suit managed languages and the expectation of runtime code generation and reoptimization and so forth. So that was designed, it was kind of a response. Remember I said before that people were designing languages to compile to Java bytecode. But then they run into this problem that Java has particular semantics, and their language may not fit that semantics well. The idea of mu was to be, among other things, language independent, language neutral. A small implementation. The original goal was simple, but maybe not your most highly optimizing implementation, might fit in 25,000 lines of code, which might be within reach of formal verification. Heroic, but maybe within reach. Right, so Steve Blackburn and his team. And this is kind of a logical extension of the MMTK ideas that he was developing. Right, and obviously the advantages they become obvious. Right, okay. Now, side trip. This toolkit idea, things are improving. What about performance evaluation? How do we know how well we're doing? So evaluating memory management well actually turns out to be fairly difficult. It's intertwined with all of the rest of the language. It's intertwined with particular applications, the benchmark programs you run. The hardware memory subsystem gets heavily involved. You know, how does your cache work? How does all the timing? And so forth. And of course, there's an extremely wide range of possible program behaviors. So the da capo benchmarks can help us tell the story of where those came from. You also need a good methodology. So the da capo benchmarks, it is a suite of benchmarks, but along with it comes methodology and methodological recommendations for how to use that suite. There's also the methodology of how that suite was developed, how it was curated. So what are these benchmarks, if you are familiar with them? So I happen to be one of the PIs on that project, but developing these benchmarks was more Steve Blackburn's effort, but a large crew of both professor level folks and graduate students at the time, 20, 25 people. And they were carefully selected to cover a wide range of memory management diversity. So we came up with ways of measuring different aspects of the behavior. How much is it allocating? How much is it changing the objects? Is it building things more bottom up or top down? All those sorts of things. What are the kinds of age distribution of objects and so forth? So you wanted to have a suite that emphasized variety of behavior instead of a bunch of programs that were technically different, but basically similar in behavior. That's not so interesting. You also needed inputs and runs that were of appropriate size. So it has to do enough memory allocation, exhibit enough behavior to be significant and interesting, but not so much that the suite takes too long to run. So they set goals there, like on machines at the time, they wanted a typical run to take 1 to 2 minutes for a particular program on a machine at the time. And for a certain size heap, it should garbage collect at least 10 times or something. So they came up with, that was part of the overall methodology, coming up with the collection of benchmarks. Right, and they tried to develop a whole set of, I think, a dozen at least different metrics that you could use to characterize the program execution and show that, yeah, these different ones were pointing, the vectors pointed in different directions. And it continues to be maintained. He's about to do a new release any day, just putting the final touches on. Now, this grew from feedback received at a site visit in the middle of this grant. It was a 5-year grant, and it was one of their larger ones. So they like to come in the middle after you've done about 2 to 3 years of work. Have some experts come in and give you some feedback. And so we complained that there weren't any benchmarks out there for us to evaluate our work. So they turned around and said, well, go make a suite. Like, oh boy, okay, what do we get ourselves into? So watch what you complain about. I might come back to you, but the end result is good. So it came with certain things like your runs should have at least a certain number of garbage collections in them, or it's just too coarse granularity to be able to say what's going on. So it would be like if they're running with one variant of an algorithm or one knob setting, it takes 2 garbage collections, so it's just this much short of causing a third one. And then the other one causes 3 garbage collections. Well, it's going to look a lot worse, but really there may not have been that much difference between them. So it's trying to avoid that kind of measurement error, or at least misleading measurement. Measuring multiple times, measuring across different platforms, different variants of the Intel processor. Oh, maybe an AMD processor, maybe also a Spark, or now a RISC-V or whatever. Different workload sizes and so forth. If you're doing sort of single point comparison using, say, only one platform, it can easily mislead you. There was a good paper about that. And another point, and I was making this more to the students that were around at ISMM, maybe would be relevant to some folks here. Measurement methodology, it isn't cookie cutter. You can't just say, oh, do X, Y, and Z, and you're fine. You always have to be thinking deeply about it. You can't just do what your advisor did 5, 10 years ago. So it requires care, considerable care to make sure you're not measuring an artifact and you're getting, something that's really meaningful. And this is just a general comment. We all need to work on upping our statistical game. It's so typical. I see papers submitted to PLDI with, and they say, well, we did 3 runs and we report the average. Why is 3 enough? Why is average a good metric? Well, yeah, or even if they say we report the mean, why is that a good one? You can make arguments, different arguments. So, okay. And then how do we deal with these complicated algorithms? How do we handle algorithmic subtlety? Well, the gold standard today is a machine check proof. And there are a few of those around. So one example is the Kcml system, which is a completely machine checked, proved ML. It's not quite exactly SML, it's kind of a variant of standard ML, as I'm told. But it's that functional language, but including all of its implementation, all of the compiler, all of the garbage collector, all proved using the Hall 4 interactive theorem proof. Another example is Pete Gammey and Tony Hoskins and other folks did a proof of a relaxed memory model, the Intel total store order model, and a concurrent garbage collector using Hall 4. Well, no, that one was in Isabel, but it's. But those are kind of heroic systems. The practical verification of your average garbage collector remains a significant research problem. We should keep working at it, but model checking is emerging as an important thing that's much more accessible. I'm seeing it with more papers. So spin and its Kcml language are one kind of model I've seen. I'm sure there's other model checking languages used for it. And I'll just mention briefly that these models express algorithms as communicating sequential processes. So it's very natural for concurrent systems, where you have very concrete variables and very concrete communication channels. You keep very small models. Yeah.
Are there correctness criteria for garbage collectors amenable to model checking?
Yeah. Spin checks linear temporal logic. And you can have sort of negative ones or positive ones, where you expect, you write a formula and you might expect it to be violated, which shows, oh, blah, blah, blah is possible. Or you put a formula which is basically saying, this should never happen. And so it has to explore and show, yeah, indeed, that it cannot make that formula true. So forth. I won't say it's always easy to figure out the right way to express something, but you can do it. Right, so a mutator then, the user program, if you will, if you're talking about trying to prove something about a collector, that would generally be modeled as something that just keeps non-deterministically choosing among a set of legal primitive operations. You load a value from the heap, modify an object, allocate an object, whatever. So you're not running necessarily a particular program. You're exploring the space of what programs could do. And then the collector, you might model that as a whole. That can start to get kind of big, or maybe more phase by phase. And the thing about model checkers is they try to be a little smart about it, but in essence, at their heart, they're exploring the whole space of possibilities of orderings of all these operations and what can happen. So you need to keep the number of variables small, because the exploration can be as big as exponential in the number of variables. And you try to use methods in how you express it and so forth to prevent that from exploding. But it's always a risk. It's typically running very close to falling off the edge of a cliff. So you generally have to keep the number of processes small. So you're not proving that this algorithm works for any arbitrary number of processes. What you show in the model checking is it worked for 3 processes. And so it's not as strong, of course, as a full verification. You just say it worked for any number of processes. But you gain a lot of confidence from it. If you say, okay, I've made where I have both concurrent mutators and concurrent collectors, maybe 4 processes, then I'm probably finding all the kinds of races that could happen in the system. I'm waving my hands a little bit, but you can see that you can build confidence. You need to keep the total number of objects involved small and so forth. And these models, of course, they're written in a separate modeling language. Kcml is the one that SPID uses. There are other ones, of course. And the pluses, of course, is this is reasonably accessible, unlike these Coq and all 4, which are complicated interactive theorem proving systems that probably have a 2-year learning curve, and still they're not easy to work with. They are not automated theorem provers. They check the steps that you tell them to do, and they make sure the steps are legal. They can do sometimes a little bit of simple figuring stuff out, but they are not finding the proof. If you find the proof, it verifies that it's a good proof. So it can be very tedious. Now, a well-designed model can be convincing and can indeed reveal flaws. And it can confirm the necessity of subtle little things like, oh, I need to put a fence in here to order these operations. And they do have the power to explore possibilities that won't come up in testing, because in testing, you tend to exhibit particular timing relationships, whereas the model checking will look at all possible orders and timings, if you will. It's not really time-based. So you are less likely to have a surprise of, oh, if I take and run on a newer version of the same processor that's in different timings, that all of a sudden things work. Now, minuses, of course, it's only models, it's not the real code. There can be differences there, unintentional maybe. And they do require this careful crafting to avoid a state space explosion. Richard can tell you about that. Struggle with that a bit. You usually bail after 20 minutes, right? Something like that. Answer us from that.
If it's got on for that long, you can usually think of a better way of creating a model.
Yeah.
Very successful.
Yeah.
I think when we used that first idea. ISMM.
Yeah, maybe.
Well, and then we developed it more in our years ago. It's very nice.
Yeah. And of course, you're putting forward particular scenarios that you're doing model checking on, and you've got to use sort of external reasoning. Have I come up with the necessary collection of scenarios to cover it? Despite these limitations, and I'll put a stake in ground and say, future work on garbage collection where people are proposing tricky algorithms, you may end up with a baseline of, yeah, we want to see your model checking of this, or we believe it. And we are starting to see papers that have that appendix of, here's my Kcml model. It's kind of nice. It's a way, you know, if you're doing algorithm paper, you can have an artifact. You can have an artifact seal. Right, and sort of a quick thing, we don't know the limits. We don't, in that, you know, we don't know what the limits on performance are. How fast can we go? Some things we do know. Well, we have some pretty weak lowercase bounds, but these don't always translate directly to the GC situation. They were more in the malloc free space. They tended to deal more with use of what I might call address space, as opposed to maybe underlying real memory consumption if you're dealing with large objects. If you get a large whole, well, if it's unmapped, who cares? You're not really wasting space, but the old bounds would think of that as wasting space. A graduate student of mine finished a couple of years ago now, worked and determined the optimal moments at which one could collect, even in a generational collector, to have the least amount of work. But you had to have a completely accurate allocation and object path trace. You have to have collected that. So it's purely a retrospective thing. And it turned out to be an order n squared dynamic programming. So in terms of the big O factor, that doesn't sound too bad. But if n is 10 million objects, n squared is still a pretty big number. So it's not clear what we can do with that. But if you kind of want to do heroic analysis of particular traces, we know how to do that. And we found that often the policy of collect when the heap is full is a good policy. It's only occasionally where you might want to select an earlier time where you're going to reclaim a lot more garbage somehow. So you can sometimes do that. If you also look at, you can draw a kind of curve. If this is heap space allowed, and then this is time, then you get a kind of exponential curve, right? So as you get out to an infinite amount of space, the program is still going to take some time to run. It's not going to spend any time garbage collecting. Right? So it approaches an asymptote. And then as you get to really tight space, it's going to zoom up because it's garbage collecting all the time. So, okay, so it has a particular shape. Well, think about it. If you're out in a region where you're not doing a whole lot of garbage collection, which is where you want to be, right? You don't want to be spending loads and loads of time garbage collecting, then moving this space knob isn't going to change the time much. If you're willing to pay a little bit of time, you might be able to reduce the space a lot. So where you are on the slope of the curve, it might really be more effective in thinking about how can we save space and saving time. When you're trying to run a lot of programs on a server, that might be more interesting. You can figure out how to tune.
There are also like cache considerations here because if you just blow up your space, you're going to have locality issues. So
right.
You're doing a lot of cache misses.
Yeah, it's a non-linear behavior as you observe. So it might be, oh, I get the space usage down a little bit by garbage collecting a little more frequently, then I may be executing within my L2 cache more and get a performance boost that way. Yeah. So we don't really know what the overall shape of the performance space is. Gosh, it's back in the early 2000s. I had a student, Naren Sachendran, who went off to IBM India, and I haven't really heard from him much since. But he did a collector called MC squared, which investigated for a block at a time incremental collection. So it wasn't fine-grained incremental at the level of individual objects, but you tended to take very short pauses. Was the idea, and the hope was that this would allow investigation of the performance surface, where one dimension is this total space you're using, another is the time overhead, and a third is what those pause times are. So we don't know what the shape of that surface in the 3D space looks like. A really great project for someone to explore that sometime. And that might be attempted for concurrent garbage collection as well. That may be harder. It's clear that we pay a premium for concurrent garbage collection. I think it's sort of obvious that to do that, you require more coordination and more interference in the memory. But there are benefits, of course, in that your system runs more smoothly with fewer pauses, really no pauses. But we don't really know how well we can do overall. And we just sort of throw resources at it. If we get it down below 5%, we can say, okay. Maybe that's good enough. Maybe we don't need to know. But just as a scientific question, we don't. Now, a little interlude. Doesn't directly have to do with GC exactly, but you'll see there is a connection. So transactional memory is another thing that I'm known for, and this is my version of the story where it came from. Morris Herlihy might not tell it the same way. He's the co-inventor. So at the time, he was working on lock-free and wait-free algorithms, one of his signature things that he does or did. And he came out to UMass kindly and gave a talk. And when we were on the way back from lunch, he said, well, can we imagine, sort of a bigger kind of algorithm? He had been looking like, a lock-free queue or something like that, sort of smallish data structures. But what about wait-free garbage collection? Is that something, does that make sense? And we got talking about it, and later we put together and published a book, Lock-Free Garbage Collection. Interesting. And in it, it didn't absolutely require, but it would have been desirable if we had a compare and swap to instruction. You do compare and swap on two independent memory locations, not a double word cast, but a two separate location casts. And there was one processor that briefly had that. It was a Motorola 88,000 or something. That's like, it's gone. Nobody's going to build that kind of CISC instruction anymore. So we said, we got thinking about that and said, it's not likely in hardware. So we said, how would you do something like that in RISC? And that ended up with this idea of hardware transactional memory. We had load and store transactional, if you will. And you had the idea of starting a transaction, ending a transaction, which then gave you the group of actions that were to be tried together. And then, of course, now have it in Haswell processors and other versions on IBM. And so that's the little story there, but that it came from garbage collection, believe it or not. Now, philosophical. Looking back, every even published ideas don't always work out and always followed up. Those who've been in the game for a while know that. So junior graduate students learn that this is true, it's okay. Doesn't mean the work is bad or the effort wasn't worthwhile. It's part of the nature of research. It's just sort of pushing out and feeling and seeing it was a good direction and then building on it. Later work might do better, might maximize over what you did. That's part of the process too. And even if the ideas don't work out, as a researcher, you're growing in knowledge and skill. So there's a benefit there. And even with a good idea, it can take a long time. Transactional memory was 20 years from the published paper to working hardware you could buy. And it was 10 years before they internally started working on an implementation. 10 to 15. A while to get with the plan and why this is a good idea. And here's a bunch of things. These are projects I worked on, this mature object space, this whole sequence of things that came from it. Here's some others, some of which Richard has worked on variants of Sapphire and so forth. So some of these are around a little bit, but some of them, they've kind of faded. There's a paper title out there that nobody's working on. Right, there's some others. And lock-free GC. I guess things like that show up in the concurrent GC world, trying to avoid lock. But versus, let's say, the MMTK and JAX RVM and so forth, now those were influential. And some aspects of them are still around. Transactional memory is still around. So, some things end up having some impact, others less so. Now, of course, GC field as a thing has been broadly successful. It's now assumed acceptable in many mainstream languages, in fact, expected. back when I was a graduate student, it was very questionable whether any mainstream language would ever support garbage collection. It was a niche language, Smalltalk, Lisp, it's a language that AI people are using MIT called Muddle. So various things like that, but it was not expected to become a mainstream. Yeah, it did. And it's even kind of an option in C++, which would have been heresy. And furthermore, along the way, we've achieved the holy grail. There are deployed real-time collectors, systems that have garbage collectors in them that run, real aerial robotic platforms, large drones. It's pretty amazing. Now, this is not to say explicit memory management, malloc-free. It still has a continuing role, and I think it will. Now, Rust tries to push the envelope there, being somewhat automatic, not having true garbage collection. I'll just say my opinion is, when you try to code in Rust, that part of the language is not easy to use. It works, but it's not easy to use. I'm not even convinced that the overhead is great. Well, I'd say, when I'm trying to do effective programming, trying to write lines of code to make something work, automatic memory management is simple. It's probably more cost-effective for maintaining and writing programs that have a lot of features. Certainly, there are environments where you can't do that. There's certain kinds of embedded systems, but you have that kind of environment, you can use garbage collection, I'd say use it. Okay, so the challenges and opportunities that remain, its limits of performance. We have emerging new domains, non-volatile memory, byte-addressable persistent memory, garbage collection over that. Quantum computing, what does that even mean, garbage collection? I have no idea. The whole space of heterogeneous processors. Richard and I have been involved in a little project I'll talk about in a second, related to that. New language features. People are always coming up with new ideas. Massive data sets. How do you deal with Spark type data sets and so forth? And continuing to realize and expand that toolkit approach. I think there are wonderful opportunities there. And then try to give people a sense of some things I'm working on now. So this is a project with Richard, and the intuition is garbage collection tends to be memory bound, right? You're accessing a lot of memory. So you're going to put stress on the memory, the buses, all of that. So maybe putting a processor closer to the memory to do the GC work is a good idea. Doing GC away from the hosts themselves also avoids disturbing those host caches, because you walk over the whole heap and all their caches kicked out. Now the challenge, though, is if you're over on the memory side of the memory bus, you're not in the coherence domain of the caches. So you're non-coherent with the main processor caches. Because the bus is in between, so it separates the processor and memory. So it makes coherence unlikely, just because of the communication necessary for it is difficult. You might be able to do it sort of one way, where if the PIM has a little cache, and then the store makes it all the way to the memory, you might be able to update the PIM's cache, but you can't effectively update the other. Right, so what we've coded up so far is a mark sweep, but it's concurrent. Well, we can run it, stop the world or not, or concurrent or not as we wish, but the interesting direction is concurrent. Right. And right, so we did marking on the PIM, and at least the reasoning we've had so far suggests that doing sweeping on the PIM wouldn't be that helpful. That might turn out to be wrong. And our initial foray is non-generational, but we think we can figure out how to do generational collection as well. Richard has done yeoman work model checking the algorithms, and some preliminary results suggested that this works. But I'll just say here's a little curve in the research road. I've been getting what looked like really good results in the Gen 5 simulator. I went, woohoo. Well, it turned out I was using a very simple processor model and hadn't really thought very deeply about it. A very simple in-order processor. If you put in a more realistic model of a modern out-of-order processor, all the performance parameters shift, and it's not clear we have a benefit without changing something else around. So it's a little bit of back to the drawing board. I'm still hopeful we're not going to come up with something, but it just shows, again, all that thing about the parameter settings, checking across different architectures. Another area that I've been working on is GC for persistent heaps over non-volatile memory, like Intel's Optane DC, byte addressable memory, doing persistence by reachability with transactions, also a new-like virtual machine, and ideas to integrate with the transaction model, and also the GC can use transactions, which might be able to help us. So it starts going down some path, and some other weird mutator action happens, it can back out and retry it. So, and the rest of the system can lean on GC to help. So examples there is efficient memory allocation, in that you worry about it, you throw off on the garbage collector row getting back any allocations, even allocation that might have in fact failed because your transaction failed in the middle. You got to do some stuff and your transaction didn't complete. You don't worry about cleaning it up. Let GC do that. And it keeps your algorithm simpler. Right, so that's very much work in progress with two graduate students, one undergraduate in both down in Australia. Working on the second edition. And I updated this slide since June because we signed the contract and the primary purpose for my visit here was to get going. Right. And this is acknowledging that it takes a whole community, it takes collaboration to do good. I might have the occasional reasonable sole author paper, but mostly collaborative. So that whole, the large DeCapo grant, and a number of close collaborators I'm going to list, and if I did anybody from the list, faculty level folks I collaborated with, students, time. So, take home points. Toolkits, shared infrastructures could be a good thing. Benchmarking, methodology, statistics, these are things to devote attention to. Model checking, and maybe formal verification if you're up for it. Collaboration. Those are my key points, and I say thank you. Happy to take questions in plenary, or if you want to talk in some more.
On the model checking front, do you think it would make sense to have a garbage collection model checking toolkit? Where you sort of say, well, these are the kind of properties you really want to have. Are they things that can kind of carry over between GC implementations enough, or is there a common core?
Possibly. I hadn't really thought about it before, but I've got like 2 or 3 little model checking projects going, and we've sort of borrowed across them. So, key thing in the work that Richard did is modeling the concurrency and the weak memory aspects, and in fact, in that particular case, the lack of coherence. So you end up explicitly, perhaps explicitly modeling, the memory, the caches, the CPUs, and in this case, the processor and memory. And so building up kind of a library of these components that already have their behavior coded. Now, the overall properties, I don't know to what extent you write those up. That might be harder. And some maybe.
Exactly. I think I drew a lot on We do this processor of memory model check. A lot of models previously done for the Sapphire.
You can refer back to methods you used. Yeah.
Same sort of ideas of things that you wanted to check.
Right. Yeah, so that's an interesting
There's
idea.
some kind of core, there's some kind of core interface that you can talk about and the properties over that.
Yeah, quite possibly. Well, certainly in terms of, say, modeling a memory subsystem, say, okay, here's something that models, cache, memory, the way modern processors work, and so you don't have to figure out that all out yourself.
Core buffers.
I mean, the problem with plugging together too many components. I'm going to go.
Right. Yeah. That's where you might run into trouble. Pronoun might not be the best language for that either, but hard to say. You might need another level that's more like a macro language. Fortunately, Pronoun doesn't really have functions; it only gives you macros. Other questions? Yeah.
I'm also interested in the model checking. My question is about the scale of the analysis you do with model checking. Have you caught like biggest counterexamples you've got in your test suites with the garbage collector? You see what I mean?
What would you say, Richard? 2 or 3 objects?
Typically, we tend to have probably about 3 objects. Got mutate a process that's doing the nastiest thing you possibly can by moving pointers around.
Do you have any suspicion that that's not big enough to catch all flaws, or do you think that's definitely
I'm
good?
fairly confident about it. Yeah. Usually that kind of low, small scale where things go wrong. You fail to sort of capture that mutation. All the barriers. You're basically modeling barriers, making sure your barriers are right, capturing the information you want. Commonly, I think the most biggest we ever had was 5.
This makes sense to me. Yeah, 10 memory interactions.
Yeah.
Yeah, maybe.
And that was what we were doing the Sapphire stuff, because you've got to replicate the heat. You've got 3 objects on one side, 3 objects on the other side.
Right.
So that they stay in.
Well, there was an intriguing result, not so much in garbage collection, but related to transactions, a transactional memory proof that some people did with model checking. And they were able to prove that 2 transactions over 2 objects was enough to find any flaw. But now, could we maybe come up with a similar sort of actual proof that if we shown this for 3 threads, 3 objects, whatever, that then it would extend to any number of threads, any number of objects, that that's enough to where any problem would show up. It might be possible to do that. I don't think people put a lot of effort yet into thinking about how you can do that, which would then automatically extend certain kinds of model checking results.
It's to a full proof.
Hmm?
It can elevate the model check. Model checking.
Yeah, you might be able to. Yeah. I mean, you wouldn't be doing that in the model checker, though. That's the trick. Yeah.
We use Z3
Yeah.
and we used a QBF solver for a QBF solver and a second order logic.
Right. Well, and part of what got me down that path, I mean, it's, I suppose you could call it model checking, but I've done some earlier work, maybe 10 years ago with a student. We applied SAT solvers. It was great when you have an automatic solver like that go off and do something for you, if you can cast the problem in that form. And SAT, of course, is limited in what you can express, but in a particular case, it worked out. So I said, oh, okay. These automated tools, they have a significant place. Yes.
You mentioned at some point the issue of statistical significance.
Yeah.
People would sort of object to, yeah, why free attendance, why the average, etc.
Right.
Do you come up with an answer to that?
Well, it's going to depend on the circumstance, right? So you're doing a variety of runs and you want a sense of maybe what the best performance of one algorithm is versus the best performance of another algorithm. Then, you know, if I'm talking about times, in a case like that, I might be willing to discard outliers that are high amounts of time because they're disturbed by something. You know, some weird interrupt happened or some network packet arrived or something that disturbed the underlying thing, and you can view that as then not giving me a true measure of the best performance. I'm trying to get best, right? But maybe not trying to get best, maybe I'm trying to get typical. Then I want to see more of a distribution, and I may want to know that does this have a heavy tail that sticks out, and then some other algorithm maybe not. Sometimes you're doing algorithms to try to control the variance. In that case, the variance becomes significant. So, I don't think it's any single hard and fast rule.
I mean, the reason I asked, I had sort of a similar objection to some research I did, completely different area.
Mm-hmm.
And sort of the issue is the notion of statistical significance. This is normally defined in terms of when you do experiments of human beings, or populations of human beings where they're
Right.
where you have a fair selection. And
Or
that's
even
also
in
difficult.
physics experiments, where you rerun the experiment.
Yeah. Yeah, but then it says you rerun the experiment. In computing, you have to sort of think about, okay, what is your population? What is the population of garbage collection experiments you run this thing over? What are the realistic ones?
Right.
I mean, you could sort of think,
Well, often I
pretty
talk
much
about
strange languages.
running the same algorithm on the same processor with the same inputs. If I do that 30 times, do I get a consistent result out, and what's the variance? It should, unless it's some complicated randomized algorithm, it should come out very close all the time for that. Now, you're correct. If I want to compare two algorithms, I need to compare them under a range of situations. How do I choose the situation faster? And that's one of the points. I forget which paper it was, and I think it was Steve Blackburn was saying how there's work that he had done and other people had done that gave misleading results because they compare a particular model processor, and he takes and runs the same pair of algorithms on another model processor, and the results flip. It has a different memory subsystem, a different time. And to the extent you can, you want to run the widest variety of things in terms of platforms. You get a sense of how platform influences relative advantages. And even then you start problems like, how many different heap sizes do I run?
When you do these kinds of experiments, do you normally get sort of a normal distribution where sort of everything gathers around typical performance and sort of the weird ones are rare, or do you get some that's sort of a bit tilted where?
No, I would say it's more tilted that there's some asymptote of the best least disturbed performance you're getting for a particular setting, and then you have ones that are disturbed. So the mean is going to be close to the minimum typically. Or at least the mode, or I'm sorry, the median is going to be close to the minimum. But you may have a long tail this way. And that's why I say you might be able to justify throwing away outliers, because if you average them in, it's not giving you a sense of the typical behavior. It's pulling too far because it's skewed distribution. But the best is to show like violin diagrams. You show people the distribution. Yeah. Especially if there's only 3 or 5 runs. It's not telling you much about a distribution.
Yeah, we did sort of experiments with some area where we had sort of run the thing 1,000 times, difference in runtime is sometimes a factor in one experiment and the other, and most were very, very close to the minimum, and they were the outliers.
Right. Those are the ones that Google worries about. Most times the search engine comes back fast.
Yeah.
And most of the time, it's firing out a whole bunch of subsidiary servers, and most of them come back fast. And the question is, well, for that one that didn't, do you wait, or do you ignore the result, or what do you do about it? But they have a kind of heavy tail that they worry about, and they have a big enough customer base that once in a million things come up many times a day for Google. The other companies might be able to ignore it if they're doing in smaller volumes, but they have to worry about it. So it's an interesting problem. Yeah.
So I don't actually work in garbage collection, so this might be a very basic question. So I'm trying to understand what is the commonly used correctness criteria for a garbage collector.
Okay, very basic should be, it should not reclaim an object that you could use again, right? So
Yes.
You've got to start there. So it can't reclaim something that we would call live. It's live that could be reached and used. And then the second thing is ideally you want it to reclaim all the unreachable stuff. You want it to do it with a degree of promptness. Promptness gets into time, so that's difficult. But you might be able to say within so many number of garbage collection cycles, because the algorithms tend to run in cycles.
So formally speaking, how do you state this kind of a guarantee? So is it stated over multiple executions of the garbage collection?
Well, it can be, but we talked about the object graph. So you start with pointers that executing processes have in their variables, in their local variables in their stack, and then also global variables. That's your starting point. And then their objects have been allocated in a heap, and they have pointers to other objects. So we talk about reachability through that graph.
So you only stated over the graph which is available to you, the memory graph which you operate on, and not
Right.
as a property of the code, like as in the property of the program which is actually implementing the garbage collection algorithm. And
Well, no, you asked about what is the correctness condition, what is the criterion? And I said it has to do with the graph. And then, of course, to demonstrate that criterion, you're going to look at the garbage collector to make sure that it achieves that.
It's quite tricky. One thing, it's easy to say never reclaim an object that the program might use. What's harder to say is it will reclaim all the objects that the program will never access in the future. But there's a possibility that objects in the program might still be reachable by some path. The path that that program never takes.
Yes,
So-
we almost always overestimate in the sense we say if it's reachable by following a chain of pointers, we assume that the mutator could follow that chain, and so we keep the object away.
so exactly, so it's not just a property of the graph, the memory graph on which you operate on, but also the program which actually is going to operate on that at runtime. Because Richard said,
If you want to frame it in terms of whether the object will actually be used, but that's not the way we usually frame it. We frame it as it could be used by any possible mutator.
We assume that given any branch of the program will follow those branches.
Right. Yeah, so there's a little bit of a worst case assumption there. Yeah.
I'm just trying to understand how will I represent this kind of a property in a formal logic. Looking at it from that angle.
Yeah, well, it's graph reachability. It's a transitive closure property on the graph. Where it gets fun and interesting is in the presence of concurrent changing of the graph. And even more fun in a system, what we call weak memory ordering in modern processors, where the order in which you do stores on your CPU is not necessarily the order in which they're perceived by another CPU, which blows most programmers' minds, but it's true with modern processors, and you don't put special barriers in between. Pencils. Yeah, no problem.
So for the non-coherent garbage collection, how close is that to garbage collection in distributed systems?
It's not, it doesn't strike me as being that much like distributed systems because they share a memory space. It's just not fully coherent. Whereas distributed systems, I think of as not really sharing a memory space. They have to communicate entirely by messages. But here, the PIN and the host processors, they can access the same physical memory. It's just they have different caches between them and that memory that confuse their picture of it. Does that make sense? So basically, you have to put in cache flushes and cache invalidations in various places.
Well, I mean, from some perspective, if you look at the hardware, it's still messages being sent around. So
True.
that's why I was thinking maybe there's.
Yeah, except the messages aren't really between the processors in this case. The messages flow between processors and memories and caches. Processors on one hand and memories and caches on the other. And even in Gen 5, it gets really complicated. You can see all the different kinds of messages that can flow around. Happy to talk with you about it more in detail.
I was just curious.
Yeah.
Not an expert.
Do you have any questions in the back there? Something? No. Anybody?
Maybe I should mention we have 5 places reserved at the Café des Amis. Anybody who wants to join Eliot and Richard for dinner?
I would like to go.
Probably, it's.
I couldn't, I'm not gonna say no.
Sounds like first come, first serve. Okay.
That'd be great.
Right. Okay, thank you very much for your talk.